What are your questions?
Nothing super particular. I guess just kind of like I'm still just reviewing the stuff for the lab for today. Going over all of that and trying to get the hang of it.
Which lab is that? Are you talking about the one? Is there one due today?
Yeah, the one where it's the elements and compounds.
Oh, naming?
Yeah, naming. Just going through that. So it's like pretty simple, but some of it's a little weird, like with the rules.
Yeah, the rules are based on what makes the most sense.
Mm-hmm.
Like for the cation, you don't tell people to charge if there's only one cation for that element.
Mm-hmm.
And if there's multiple cations, you have to tell people to charge.
Mm-hmm.
So that's one of the rules. And
when I skimmed over it,
the rule is that the anion. Go ahead.
When I was skimming it, I saw something where you have to write it out and you go like kind of in this diagonal downward thing. Maybe that was just weird on the formatting.
Maybe that was just me not being able to write in a straight line.
Yeah. I don't know. I saw, because I was just skimming it kind of and doing like the prep for like those little worksheets, like writing them out and stuff. So I haven't really gotten started on it, but just kind of like looking over it.
Yeah, that's something you're going to be able to need to do. Not so much for showing me that you can do it, but a lot of the problems are just going to have names of compounds. And if you don't know what they are, you're going to be taking hits.
Yeah, that was the hardest part in my high school chemistry class. You had to memorize polyatomic ions, and I was like, come on.
There's only like 8.
No, it was like
8.
Well,
and 2 variations.
Yeah,
that's it.
Something like it's something like 22 or like 2022.
Yeah, but you don't need it. It's only 8, and then memorize the variation.
Mm-hmm. Yeah,
the variation is the same for all of them.
Mm-hmm.
So memorize 8 and 2 ideas.
Right.
It's not bad. And you know how many polyatomic ions there are?
Well, you just said there. Will they be what, 16?
No, in the world.
Oh, in the world. No, I'm not sure.
Way more than 8 with 2 variations. We're talking hundreds, if not thousands.
Right.
So we're just getting you to memorize the basic ones, the most common ones.
Mm-hmm.
All right. This is your question time. I know you have an exam tomorrow, so whatever questions you want to ask, now's the time to ask them.
Real quick, I have a question that's kind of a one-on-one question. Can we stay after for a few minutes?
Yeah.
Okay, cool.
I'm actually going to grab my notes really fast.
All right. I don't have anything prepared for today because we've gone over everything I wanted to go over. You got an exam coming up. Now's the time to ask questions.
The exam is on just chapters 1 and 2 and the labs, correct?
Yeah, that's right. And the labs, you'll notice they tie into the chapter.
Okay.
You can ask questions about the homework, even though I have the solutions posted. You may not understand the solution. You can ask about that. You can ask questions about your lab assignment. You can ask questions about problems from the back of the homework. You can ask, or back of the chapter. You can ask whatever you want.
Can we go over significant figures one more time?
Okay, so yeah, we can.
There's a bunch of zeros.
So for significant figures, I'm going to change my share in just a minute. Let's see now. Okay, here we go. Significant figures. So which ones are significant? Non-zeros, tweener zeros, and trailing zeros with the decimal. So if I write out a number like 1.20030, and we call this A, B, and C, the 1 falls under rule A, the 2 falls under rule A, the 3 falls under rule A, and those are all significant. This 0 falls under rule B, this falls under rule B, and we have the world's greatest band, ABBA. And then this 0 falls under the rule C. It's a trailing 0 with a decimal. If we look at this, this is rule A, and rule C and rule C. So this top one has 4 or 6 zig figs, and the bottom one has 4 zig figs. So those are all the significant ones. And the not significant, we have 2 rules. I'm going to call them D and E. Leading zeros and trailing zeros, no decimal. Now, when I say no decimal, the decimal is implied. So what we're talking about is if we have 4,200, the 4 is rule A, the 2 is rule A, this 0 is rule E, and this 0 is rule E, so it's got 2 significant figures. And if we have 0.00002, this is rule D, 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 and this is rule A, so it's got 1 zig fig. So that's how you count them. Any questions about which figures are significant and which are not?
Is the only difference between the 4,200 with the decimal and the 4,200 without the fact that it has a decimal?
Right, and that's why the rule is with decimal and no decimal.
Okay.
That's the distinction we make. So is that kind of what you wanted for significant figures?
Yeah, thank you.
Yeah. No worries. Who's next? Come on, you must have questions. Don't be afraid to ask.
I had another question.
Go ahead.
Are we going to be provided with a periodic table, or is there stuff on there we're supposed to memorize? I can't remember.
Yeah, there is stuff you're supposed to memorize, but you will be provided with the periodic table.
Okay.
So for instance, if you, on the periodic table, you'll be given the symbol, the atomic number, and the atomic weight. And that's it. So if you don't know that lead is Pb, that might hurt you.
Okay.
So I did this in some other lectures, but the elements you should know are 1 through, you should know 1 through 40, where if I give you the symbol, you know the name. For the rest of them, I'm just going to give you the symbol. You should know silver. You should know tin. You should know antimony, iodine, xenon, cesium, barium. You should know lanthanum, platinum, gold, mercury, lead. You should know polonium, and you should know radon. You should know francium and radium. You should know actinium.
Hold on.
You should know uranium, plutonium, and americium. And these are the ones that you should know. So there's 40 plus whatever these are, 5, 9, 6. So another 20. So you should know 60 of them. And they're not too bad. There's some that are odd, like how you get mercury out of Hg, who knows, right? Or gold out of Au, or antimony out of Sb, or tin out of Sn, or silver out of Ag. But then there's others where it seems to make sense. Xenon is Xc, radon is Rn, cesium is a CS, francium is Fr, radium is Ra, actinium Ac. So a lot of them do make sense, and some of them don't.
Oh, I have another question. So yeah, I was going through the lab, the one on mass spectrometry, and I was kind of confused on the last question when you were talking about qualitative versus quantitative. And
Okay, well, there's a problem actually in the book that asks for the spectrum of copper chloride, copper 1 chloride.
Mhm.
So here's copper 1 chloride. That's the formula.
Mhm.
And copper has 2 isotopes. One of them is copper, let me see.
You're not sharing screen.
Oh, thank you. Okay, so you want the mass spectrum of copper 1 chloride. There's 2 coppers, 63 and 65, and there's 2 chlorides, 35 and 37. And the book even goes to tell you the percentages for each of these. I don't remember what they are, but I believe that this is 76%, or let's just call it 75, and this is like 25%. And for these two, it's about the same but reverse. So it's about, no, it's 75%, 25%, something like that. I don't know the precise numbers. The book gives them to you. So to figure out the qualitative mass spectrum, you would have to figure out all of the peaks that you would get. You could get a copper 63 and a chlorine 35 like that. I have to pause for a moment and get another pen because my ink is running out. Where did I put my pens? Guess I'll just use one of these and see how it works. Okay, so this guy here, if you look at it, it's going to have a mass of 98. And that's going to be the mass to charge. You could have a copper 63 and a chlorine 35. And when you add, oh, I already did that one, 37. When you add these together, you're going to have 100 for the mass to charge. You could have a copper 65 and a chlorine 35, and that has a mass to charge ratio of 100. And then you could get a 65 copper and a 37 chlorine, which has a mass to charge ratio of 102.
Mm-hmm.
So right away, qualitatively, we can do this and say that this is the intensity, and this is the mass to charge, we're going to get three values, 98, 100, and 102. And so I'm going to evenly space those because they go in twos. So this is the beginning of your qualitative. The qualitative, you just basically don't want to take a calculator out.
And then how are we getting the 98 and 102?
63 and 35 is 98.
Oh, okay. Easy, easy.
Yeah, if one of them weighs 63 and the other weighs 35, the mass to charge ratio is the sum of those.
Got it. Cool.
Just like with a chlorine mass spectrum by itself, you get two peaks, one at 35 and one at 37. So where do these come from? Well, that weighs 35 and that weighs 37.
Got it. Okay, perfect.
So what happens when there's two of them? Well, it weighs as much as the two put together. Now, we can kind of estimate how big the peaks will be by taking this number and multiplying it by that number. So I'm going to say that this is the same as 70 times 80. Only I'm not going to do 70 and 80. I'm going to use 7 and 8. What's 7 times 8? It's 64 minus 8. 56.
56. Sorry, I just
And here, what's 8 times, I rounded this up, 8 times 2.
8 times 2, that's 16.
And here, these two, what's, I'm going to do it the other way. What's 3 times 7?
21. 22.
Okay. And what's 3 times 2?
6.
So I expect the peaks to be something like this. So that means this is going to be my 100. It's the biggest number. So my 98 is going to go right to there. And then this one is going to be not quite as tall as the biggest peak. You know, if this is a 51, 41 would be probably, or 56, 41 would be something like that. And 6 would be like that. So there's your qualitative mass spectrum.
Okay, perfect. Yeah,
You don't need a calculator.
that's awesome. Yeah.
Okay.
Yeah, that mass spectrometry lab really, that one really got me.
There's a lot of math involved. So one of the reasons we require people to have algebra in this class, you'll see later that there's a lot more.
Yeah. Well, that's the thing. It's like I'm too smart not to know it. Like I'm taking trig right now.
Oh, trig is a different animal than algebra.
Yeah.
Trig is useful. Algebra in general, all the parabola stuff is not very useful.
Yeah.
But the other stuff where what you do to one side of the equation, you have to do to the other, that's very useful.
Yeah.
The golden rule of algebra. Parabolas are not the golden rule. Parabolas are what engineers like to study. And mathematicians and engineers are like this. So naturally, mathematicians gravitate towards teaching. I should say, engineers and mathematicians are like this. So mathematicians love teaching parabolas because engineers love them. Okay. That doesn't mean that parabolas aren't interesting. It just means that they're not that useful in chemistry or other sciences. Really good in engineering, though. So if you want to be an engineer, you pay attention to algebra.
Yeah.
Okay, who's next? Feel free to jump in.
Charlotte is asking in chat if we can review the concepts of chapter 1 for like density and physical versus chemical change.
Okay, yeah, sure. Am I still doing my share screen where you can see my hands?
Yeah, you are, Tony.
Excellent. Okay, so if we want to look at a physical change, The ultimate definition for physical change is there's no change in the formula of the substance. So that means that you're doing things like you're halving it. So you can go from 1 pound to 0.5 pounds. You're not changing the formula of the substance. You could change the state. So this little triangle means change. So if you go from a solid to a liquid, you're not changing the formula. Or a liquid to a gas, you're not changing the formula. Or backwards, liquid to a solid or a gas to a liquid. Or if you go from a solid straight to a gas or vice versa. These are called changes of state. So an example of a solid to a liquid is ice turning into water. An example of a gas to a liquid would be steam turning into condensation. An example of a solid turning into a gas would be dry ice turning into carbon dioxide gas. There's no change in formula. So that's a physical change. And then there is a chemical change. And I'm going to leave a little spot there. A chemical change is there is a change in formula. So here, if we take H2, and that's a formula, and we add it to O2, that's another formula, and we make H2O, that's another formula, there's a change in these two formulas where the atoms come together like that. So ultimately, this is how you know whether you have a physical change or a chemical change. But what if you don't know the formulas of the things you're playing with? There's another way that often works. It doesn't always work. But here, this would be a difficult, or I'm sorry, wrong one, difficult to undo. I don't know if that's a word, but I'm going to write it down. And this is going to be easy to do or undo. Is it easy to half something and then to put it back together? Well, certainly, especially if it's like gold, because you could just melt it back together. It doesn't work so well with a sandwich, because once you cut it in half, you can't put it back together. But cutting a sandwich in half is a physical change. You're not changing the chemistry of any of the components. So that's why I say that this usually works, but not always. And here, that's supposed to be difficult, not difficult. For instance, if you bleach your shirt and it has now got a whitish bleach stain on it, that's difficult to undo, and therefore it's a chemical change. So are there any questions about this before I move on? Because there's more to talk about. Okay. So there is also the physical property versus the chemical property. So physical property is going to be one that you can determine without changing the formula. So that's my symbol for without, WO. And usually you can do this without changing the substance. Cutting it in half, putting it into a larger container. Chemical properties, these are determined by trying to change the formula. So if we take a look at a chemical property like, does something react with acid, or does something react with well, yeah, let's do acid. So you have hydrochloric acid. This AQ means it's dissolved in water. This AQ means it's dissolved in water. If you do this reaction, I'm going to put a 2 here, you'll get H2O liquid plus sodium chloride aqueous plus CO2 gas. So if we were asked about this and asked, is this a chemical change or a physical change? What would we answer? And the answer is, well, there's HCl here, but there's no HCl here. So therefore, just looking at HCl, this is a chemical change. We would find that to be the case here with this second compound. It's changed. So this is a chemical change. Now, are there physical changes that happen here? And the answer is absolutely. You have these things that are dissolved in water, and then all of a sudden you have this thing that's not dissolved in water. But a physical change, the way we talk about it, is there's no change in formula. And so here, when you have chemical changes and you have changes in formulas, is it possible to have changes in physical properties too? And the answer is absolutely. So that's why the fundamental difference between chemical and physical is physical, you're not changing the formula, and chemical, you are changing the formula. So let's say that you do some sort of experiment and you have these two solutions, and you mix them together. So I'm going to call this solution A and solution B, and this one is clear and colorless, and this one is red and clear. So clarity and color are two different things. Clarity means can you see through it? If you can, it's clear. If it's not, it's cloudy. And the color is what color you see. So a lot of Kool-Aids, if I remember right, you can see through them, so they're clear. But things like milk are cloudy. Okay, so if you mix these two together, and you get a solution that's pink, you know, what would be our idea of what happened here? Is this a physical change or a chemical change? Well, my idea would be that if it's clear and colorless and red and clear, when you mix them together, it would turn pink, as long as this stays red and this stays clear. So when they mix, they mingle a little differently, so it looks pink instead of red. So I'd call that a physical change. That is to say, formulas haven't changed, because presumably we could separate this out. And I may be able to do this. Let me see. No, I can't. I thought I had a red pen nearby. Okay, now let's say that this is what happened instead. It turns blue. And you get stuff bubbling out, and you get, so this is a gas, and here you get a solid in there. So here, if you take a look, the fact that it changed color means that it's probably a different substance, because each substance has its own set of properties. And here, if these things stayed with their own set of properties and just a physical change, they shouldn't turn into a solid, and they shouldn't turn into a gas. So probably when these two mixed together, they reacted. And when they reacted, they made this solid, this gas, and this blue color. So this is a chemical change. And notice that to see that there's a chemical change, we look for physical changes. But we look for physical changes that would be really hard to undo. Like, how would you turn this blue back into red and clear? How would you take this solid and make it dissolve? Or how would you take this gas and shove it back in there? So this goes back to that, if you're looking at things, how do you know? Well, you ask yourself, could this be undone fairly easily, or would it be really, really tough to undo? Really, really tough to undo. This one, presumably you could undo it somehow. Okay, so those are physical properties and chemical properties. And if you look in the book, there's some problems that deal with this. They're around page 50 or so. At least I think they're around page 50. Oh, maybe they're more around page 100. Oh, 24. They're around page 24. 50 is the end of that chapter. So if we take a look at some of these things, physical and chemical properties, in each case, decide if it's a physical or chemical property. The color of an element is orange red. Well, if you cut the element in two, will it still be orange red for each half? And the answer is yeah. Physical. Iron turns to rust in the presence of air and water. If I remember what rust is like, is that when things are rusty, they get crusty and powdery. They crumble. Iron does not crumble when it's not rusty. So the fact that the iron is malleable and the rust is not tells me that probably it's a chemical change, because it's hard to undo. If it was easy to undo rusting, we wouldn't have rusted cars. We wouldn't have rusted automobiles. That's the same as a car, isn't it? Trains. We wouldn't have rust on the sides of houses or sheds if it were easy to undo. Hydrogen can explode when ignited in air. So here, if we look at figure 1.16, I'm interested to see what they have. So here's what they have. And if we look at this figure, hydrogen exploding, you'll notice they have these H2 gas molecules and these O2 gas molecules. Well, actually, these are all O2. These pink ones are just farther away from us, I guess. And here's your H2 molecules. You can see that the formula changes. So if you look at the image, you know that's a chemical change, because O2, H2 turns into H2O. So what I'm trying to point out is that we use a number of different strategies when we're going through these. For C, we could actually look at the formulas. For B, we have to think about how easy is it to do or undo. For A, we ask ourselves if is the orange-red color dependent on the bromine's chemical properties, or if we cut it in two, does it change or not change, type of thing. Okay, so that's how you work with this kind of stuff. I'm not sure if I got the question answered. Did I?
Charlotte said yes in the chat.
Okay. All right, Charlotte, you're making me open my chat window. I got my participants window open. Oh my, I don't have room on my laptop. It's only a 13-inch laptop. All right, who's next? Anything at all. It's all fair game.
So in terms of what we need tomorrow, like what should we have before we start the exam? Like paper, a calculator?
Oh, sure, I can tell you that. You should have paper. You should have a calculator. You should have your 3-inch by 5-inch card, both sides. Do you remember that?
Yep.
You should have photos of your 3-inch by 5-inch card. Might as well have that done before the test because I'm going to ask you to send them in. You should have a pencil. I would use a pencil, not a pen, so that you can erase things. What else should you have? Oh, you should have your wits. You should always carry your wits about you. So those are the things you're pretty much allowed.
Okay, thank you.
You bet. Oh, and I guess I should say your computer. And you're going to have to use Chrome. Because what's going to happen is when you take the test, I'm going to record you. And it's going to show me what your keystrokes are. It's going to show me you taking the test. And you know, when I look at the recordings, first of all, I don't look at them unless I look at your test and I notice that there's something irregular. And then I look at the recordings and I look at, well, what are the keystrokes? What are the windows they opened? And if you're opening stuff that says, if you open a window that says, how do I do this problem? Help, help, I need it now. You cheated. Game over. If I look at the video and I see you looking away from your paper all the time, I assume that, or looking away from the computer all the time, I assume it's because you're writing stuff out on a piece of paper and trying to solve the problem. So it doesn't bother me if you're looking away from the computer all the time. No one can take a test and look at their computer the whole time. That's stupid. So I expect you to look away. But on the other hand, if you look, you know, if I see you looking up and then nodding your head when someone's talking to you, that's a clear indication something's going on. It also records audio, so if someone were talking to you, I'd know about that. So that's why we do the Chrome, is to just keep you on your toes and make sure that you're not doing anything you shouldn't be doing. Unfortunately, I can't make you take it all at the same time. So, you know, presumably one person could take the exam and share what they've learned with someone else, but I can always tell when that happens also. And I won't tell you my trick. I'll just tell you it's pretty easy to see. And the deal with cheating is that I've had to call it out a few times in my career. Not too many times, because most people are just quite honest. So this shouldn't affect you one bit. But if you do tend to stray, usually I can pick up on it. And usually I just give you a 0 for the exam. That's it. I don't care if you didn't cheat on the rest of the exam. You just get a 0 because it's easier for me to grade and it teaches you a lesson. And if you fail one exam, that doesn't mean you will fail the class. So it's just a lesson learned. Don't do it. But I'm probably talking to the wrong people. You guys are probably just fine. Okay.
Yeah. I had another question.
Yeah.
I was looking over the announcements again. So I remember seeing something about hydrates and how it was fair game for the exam. I said, oh, wait a second. I might want to go over that a little bit.
Yeah, we just talked about the hydrates lab yesterday.
Mm-hmm.
And hydrates are fair game for the exam. So a hydrate is basically an ionic compound with H2O associated with it.
Mm-hmm.
So you should know how to name hydrates. So for instance, this guy here, it's called cobalt 2 chloride because of the COCl2. And then it's called dihydrate because of the 2 H2Os. And if you had this, that would be cobalt 2 chloride, because you can see it's the same formula as the one above, but it would be called hexahydrate. So I'm not going to go through all the different levels of hydration, but you should know 1 through 10. So 1 would be mono, 2 di, 3 tri, and so forth and so on. Plus there's one more you should know. So this is a compound I know of. It's called calcium sulfate hemihydrate. So how in the world are you going to remember hemi for half? And the answer is think hemisphere. Hemisphere is half of the earth. There's a southern and a northern. So hemi means half. So if you happen to be one of those people who really likes Dodge trucks because they have Hemis in them, it's only half the engine. And you shouldn't like Dodge. Okay, that's not why they call them Hemis. But, I have no preference for a truck. Dodge, Ford, Chevy, Toyota, Nissan. I think I'd probably have a Toyota. They tend to be pretty reliable. But I don't want one. Do you know why? Because they get about 10 miles to the gallon. Why would you buy one of those things?
Plus, once you have a truck, everybody's like asking you to like move stuff because you're the guy who has a truck. So.
Oh, really? Well, I've never had that happen to me because I don't own a truck.
Exactly. That's the best reason not to own one. It's like no one bothers you.
Okay. So you should know how to name them, and you should know how to get the formula. So this is something I did in yesterday. So it's fresh in my mind. But if you have a hydrate with cobalt chloride, and notice you don't know how many levels of hydration there are. Is it 1? Is it 2? Is it 3? Is it half? If you heat this, you can actually remove all the levels of hydration completely. So this is going to be a solid, this is a solid, and this is a gas. And this is like a, this solid, it doesn't really feel wet. So my example I'm about to give you is not perfect, but we'll go with it. A potato is pretty solid, right? And if you heat it up, eventually it becomes a shriveled thing because all of the H2O has left it, right? So that's a similar type of thing here, only here we have a change in chemical formula. So this is a chemical reaction. So if we start with 0.99 grams here, and all of the gas escapes, and we weigh this at the end and we get 0.54 grams, we can figure out the mass of the gas because the mass of the hydrate, that's the above, should equal the mass of the dehydrate plus the mass of the H2O. So that's the law of the conservation of matter. So that means that the mass of H2O is going to be the mass of the hydrate minus the 0.54, which is 0.45 grams. So that's how we get that number. Okay, that being said, what do we do with these numbers now? So I'm going to have to get out another piece of paper here, or write on the back of one. So we take our 0.54 grams of cobalt 2 chloride and we turn that into moles of cobalt 2 chloride. We take our 0.45 grams of H2O and turn that into moles of H2O. And then we use these things to get the formula. So to get the molar mass of cobalt 2 chloride, you simply add up the masses of each of these, which is 58.93, 35.45, and 35.45. And that adds up to 3, carry the 1, 8, carry the 1, 9, carry the 1, and 12. So 129.83. So you take your 0.54 grams of cobalt 2 chloride times 1 mole of cobalt 2 chloride over 129.83 grams of cobalt 2 chloride, and you get 0.004. And I just remember this because it's fresh in my head. And I want to say it's 416, but I'm going to double check. Yep, 0.00416. But since this is 2 zig figs, it's only good to here. I don't want to leave that like that because it looks like carbon monoxide. And here I want to say it's 0.250, but I'm going to double check. Or 0.0250. Good thing I checked because it doesn't look like it is. Oh, it is 0.0250 mole of H2O.
Tony, I have a question.
Yeah,
So how come on the top equation, it's only 2 sig figs if the 129.83 has more? Is it because we use the furthest to the left? Like that
because of
number?
this one. This
Okay,
has 2 zig figs. This has 5, so this only gets 2.
gotcha. Okay, I remember now.
Okay, and leading zeros don't count, so
Right.
this one is also going to be good to write there. And now you use these two to get the formula, and then here's how you do it. Take the moles of water and put that on top. Take the moles of cobalt 2 chloride and put them on the bottom. And since this is only good to here and this is good to here, I'm going to round to 2 zig figs. And I get 6.0 mole of H2O because that doesn't cancel with anything, so I keep it, over 1 mole of cobalt 2 chloride. So how do you write this as a formula? And the answer is you write it as CoCl2.6H2O. And the name of this is cobalt 2 chloride hexahydrate. All right, Jacoby, are you good on that?
You're muted.
I'm muted.
Sorry, no, I am. Sorry about that. Yeah, it makes a lot more sense.
Okay, so you're going to be doing a lab like this where you will be weighing out the starting material. You're going to dehydrate it, and I give you some suggestions on how to dehydrate it in those little
Little ampules.
Q&As that I did yesterday.
Oh yeah.
You can do it in the oven or the stovetop, and you want to read the lab.
Mm.
It's not that hard to do. You can actually do it while you're studying.
Awesome.
In other words, there's a lot of downtime where you just put it in the oven and wait for it to bake.
Mm. Yeah, I saw hydrates and I was like, oh, that's a scary long word. And then I was like, okay, it's not that bad.
No, it's not that bad. You know, drywall. Drywall is made out of 2 pieces of cardboard, and in between you have this solid stuff.
Mm.
That solid stuff is a hydrate.
Right.
And,
Yeah.
you know, they call it drywall, not mushy wall. So even though it's got H2O in it, it's not a liquid or a slushy thing. It's a solid. Hydrates tend to be solids.
Cool.
All right. Who's next? We've got some good questions here. We've got that mass spec question. So you guys hopefully understand that a little better. We got questions about physical change, chemical change, that type of stuff. Significant figures. Anything else I can help you with?
I'm good.
Okay. So here's your strategy for taking the exam is make sure that you're not real nervous before the exam. So the best way to do that, but also be alert. So my suggestion is before you take that exam, go for a little 10-minute walk. That will get everything kind of thinking. You know, if you go for a walk, one of the problems I have when I exercise is that I start thinking. And then I naturally start thinking about work. And I hate thinking about work when I'm walking or when I'm riding my bike. So what I will do is I will put earphones in and I don't listen to music because when I listen to music, I start thinking about work and then I just missed like 6 songs. I'm like, what the hell happened? So when I go for walks or exercise, I listen to audiobooks because you can't check out on an audiobook and they start talking about, you know, Mark 5 minutes later and you have no idea who this dude is. You have to stay invested in your audiobook, which means you don't think about your work, which means it's relaxing. So, but nonetheless, it's really the physical part that helps to relax you. So give it a try. Take a 10-minute walk before your exam and then take your exam. And if you can't go for a walk, then you do something else like, you know, maybe for you, it might be, I don't know, walking around in your house, folding some laundry, any sort of physical activity right before you do your exam for just a short amount of time is going to help your brain to think better. So I would do that. Make sure you have your 3x5 card. Make sure you have plenty of pencils on hand because you don't want to have to sharpen one if you need another one. Make sure you got a nice eraser and you got a relaxed atmosphere. And hopefully, if you have other people in the house, you have used your duct tape carefully and put them in that closet. But, you know, don't put duct tape over their nose and mouth because that's a bad strategy, okay? I'm just talking about hands and feet. And you guys know I'm kidding, right? So what you really do with people who might interrupt your flow is you get the babysitter out, which could be grandma, could be your significant other, could be your aunt, a close friend. But never your chemistry professor. Okay? They will not take care of your children while you're taking an exam. So I just want to make that clear. So do you have any other questions, people?
I have another question.
Sure.
Will the Proctorio thing ask us for our ID again, or is it not going to do that?
Yeah, probably will.
Okay.
Ask you for your photo ID and you show your school ID or your driver's license, or I guess you could show your passport. But you know, when you show your ID, I'm fine with also you covering up any sort of numbers that you don't want me to know, because I don't want to know your social security number. It's not going to help me unless I know your PIN number too. Okay, is that clear?
Yes.
So if you're going to give me your social security number, give me your account number to your bank and your PIN number, and we're good. And if you don't want that to happen, then cover up your social security number, for goodness sakes. Don't give it out. When I was a kid, you used to give out your social security number like candy, and that was a bad idea. Okay. What else can I help you all with? Okay, we're going to call it quits. I will post this in about an hour when Zoom is done processing it, and then YouTube has to process it. You should be trying your quiz today. Remember, it's multiple choice, 10 points. And you get to take it again and again and again if you want to get more points. And it's with Proctorio under some pretty strict conditions. So it kind of gets you used to things. So if you do get kicked out for doing something, you want to make sure you don't do that on the test tomorrow. So the other good thing about the quiz is it's a good practice to find out what things will kick you out. And there you go. So without any other questions, let's go ahead and say goodbye to everybody.
I do have a question, but it was
you're gonna
just
hang
for-
on.
it was
You're
just
gonna hang
you
on, but we're gonna do something special. So everyone say their goodbyes.
Bye.
Bye.
Bye. Okay, so hang on just a second, Jessica.
Okay,
What I'm doing here, Jessica, is I'm stopping the recording.
perfect.